Okay, so I'm recording this video separately from the stream I just did because I had my microphone off the entire time and I had no idea. It should now be on, but I did a whole stream for like 2 hours talking to myself, which, I mean, is really no different from what was actually happening because no one was there to watch it. So, be that as it may, I kind of wanted to show kind of just a summary of what the stream was about. So I implemented a way to get a behavior similar to the Python named arguments list in C++ 17. As you can see, I've got compiling code in my Godbolt here. Let me turn on code execution so we can see a little bit more. So I made this dummy object here. It has one constructor that kind of has the argument list like you'd expect, like a typical class. I have 3 arguments, 3 members, and I'm using each argument to initialize one of those members. And I have this second, a lot uglier constructor that takes this first weird-looking argument named argst. I'll explain that later. And then a variadic pack of arguments that is then forwarded to a bunch of these functions that are then used to initialize each member. And so I'm using both here. So first version here, I'm supplying 3 arguments like you would typically. They're positional arguments only. That's what you expect in C++ or C. And then this second example here, I'm actually using named arguments, which I'm going to have to explain kind of in more detail because how we got here was a little more interesting than what you're actually looking at. But a couple things to highlight. So here I'm using this to initialize arguments B, A, B, and C in their respective order. But you notice here that the named arguments corresponding to each of these fields is actually flipped around. So I'm supplying the value for B first, then A, then C. And I could do this pretty much in any order. Doesn't really matter. And our named argument implementation is going to be able to handle it. And this last example, I'm only supplying 1 argument. I'll explain later that this is like a required named argument. And then a junk value, which on stream you would have been able to hear me lamenting about it. I couldn't figure out a way to handle junk values that weren't part of the expected keys, but we could just do this. And internally, we came up with a way to supply a default argument for arguments that allow defaults. So here C and B can be handled with default arguments if we don't supply them, but not A. So if I get rid of A, we get a nasty compilation failure. It's actually down here now. See all this nasty garbage? Any compilation failure where there's like templates or compile time tricks involved, of course, could be absolutely ass. But yeah, I guess let's start to break it down. So how did I even get to a point where I could say some key equals a value? What is even happening here? Because obviously this doesn't look meaningful, or it's not immediately obvious, I think, what is actually happening here from a C++ standpoint. So the first thing I actually want to explain is this underscore name syntax. So I'm using this here to do the following. Supplying a key, then using this underscore name syntax, and then supplying a value, which could be literal, an actual like other variable. Doesn't matter. It'll get forwarded to the initializer list here to initialize one of our member variables. So what is underscore name is the question. So I got to go all the way to the top here somewhere. It's weird. I'm actually like reverse engineering the stuff that I previously engineered in the stream, so bear with me if you're searching around. Where the hell is this? Okay, here we are. Underscore name. What this is a user-defined literal. When I first saw this shit, I was like, what the hell even is this syntax? It was introduced in C++ 11, I think. I'm not even gonna look it up. I'm too lazy. I'm burnt out from the absolute annoying fact that I didn't record the actual audio in the stream. But okay, this is where we are. So there are a bunch of flavors of this. Some of them take arguments. So typically if you want to like convert a string to something at runtime, or you want to use it for numeric types to convert with like units or something. So it typically uses for a user-defined version of something like, you know, the f suffix on a number. This implies that it's a float literal. You could make your own float literal that did something else. So let's say I wanted to call it milli floats or something stupid, or just mf. This would convert this to some value, some milli float value, using one of these operators. But here we're using a really special version of the user-defined literal. What it's going to do is expand a string into a variadic pack. So like, let me take my comment from down here. What this does is it takes key and expands that into character, and then the characters that follow, like this. And what this allows us to do is to perform, you know, recursive compile time stuff on this variadic pack. So you can see how this could be like super useful. How we're using it here is that we're going to take this string, expand it as a variadic pack, and at compile time compute a hash value for it. So the hash value is going to be used to do some sort of associative lookup between a key. So we're supplying a hash here. There's actually a separate user-defined literal for hash, which just computes a hash value. I'll explain what this user-defined literal does differently in a bit. But here, what this does is compute a hash for A, or ABC, whatever, some arbitrary string. And then we're going to use that hash to compare against a list of key value pairs that we're going to supply to our constructor here, and see if we can match any of the hashes in those key value pairs to the hash here. And if we find a match, then we'll say that that is the value we're going to return from getarg to initialize m_a with. So I mentioned there's actually another operator, user-defined literal operator, defined above. I'll come back to this one because this is the one doing most of the legwork for our little number right here, making this assignment-looking jive even possible. Let's go back to the simpler user-defined literal. It's just computes a hash. So let me go back down to this. Where are we even at? Okay, we're here. So the purpose of this is to compute a hash based on the string expanded as variadic pack. The other one does a little bit extra, but also computes the hash. So how do we even compute this hash? So I looked up just a basic string hash function. I found this one at this link. You can check it out. I'll put all this code in like a gist on GitHub. It's already there, but I'll link it in the video. I don't necessarily care how good this hash value is, how hashing function is. I'm sure that some combination of characters is going to result in a hash collision that would break this down, but I don't know, there's probably other ways without a hash function to just compare the characters directly that would avoid collisions anyway. But we don't exactly care, right? At compile time, the compiler is going to try to do some sort of some matching scheme anyway that could be easily replaced if you wanted it to. But here I used a hash because what this was inspired by was like a compile time associative container. And so we're doing the same associative matching based on a hash to find a value type that's associated with a key. So what I wanted to do first was take this function and turn it into a compile time version. And the way that I implemented it was this helper struct that will compute the hash recursively. So here I have just a forward declaration. We know that we want to take some initial value for the hash, that's what this is. And then we want to compute a hash for some variadic pack. So I know there's like an auto template type deduction thing in C++ 17, but I want the old method where you supply like a type, and then if you want to supply a variadic pack of that type, you would just say t ... values, as opposed to just like this. I mean, frankly, I don't think I've ever even used auto type deduction for template argument packs yet. I haven't really seen the need to. This works just fine. Okay, so to actually do the recursion, we need to define a recursive template. So here I define a partial specialization. Again, it takes a hash value, the type of the value pack that we're unpacking, and then we're going to specify a couple of extra template arguments to specialize on, cur, next, and remaining. And what this is going to do is basically basically supplied in place of values, and we're going to unpack it such that we have access to the first two values, and then we'll just account for the remaining values in this remaining pack. So this is like the tail types. This will allow us to access the first two values. So that's good. We're only going to use the first value though to update the hash. So as the hash is defined, we're going to take the hash value, the current hash value, bit shift it right by 5 bits, add it, then add the next value. This is our updated hash value. And then the recursive part comes in where we take our updated hash value, supply it as a template argument to this template again, and then we pass in next and the remaining values to then expand out the hash until we reach a termination point. So the reason why this is partially specialized on two values from the variadic pack is that we want to have a base case where we just have a single value left, which if we just did something like this, it'd be ambiguous because this could just evaluate to nothing. So we have two explicit arguments that we're extracting from the pack, and then in our base case we just have a single argument that we're specializing on, where we just compute the hash again, but this is where it stops. So if we just had a single type, it would take our initial hash value, do the same operation on it, add it in, whatever, that's our hash. And so that's what's going to get evaluated when here we have no remaining arguments left, just the next argument. And that's where this terminates. So now we're back to the point where we can use our user-defined literal to get a hash value. So what we do is we define an initial hash value called a basis, or basis offset, or initial hash, doesn't even matter. I just set it to something funny. I usually like to use this as my initial hash value. I supply it as the first argument. This type T gets deduced. It's going to be a character when we supply a string. And then we're going to run the hash on the variadic pack of characters. And this is going to be our hashing function for a compile time string. And we know for sure it's getting evaluated at compile time because these are all template arguments. I mean, if they're going to be evaluated, it's going to be at compile time. And if you want to prove it to yourself, you could just do like standard cout some string hash, and the assembly for this is just going to be like MOV and then a long unsigned int equivalent for this. And so we're going to use this everywhere. We're going to use this, at least we're going to use hasher a bunch of places. This hash is only being used in one spot right now. Here. And then we're using the other user-defined literal name when we supply arguments here. So name is different. Name is a lot different. Instead of returning the hash directly, it's going to wrap the hash in a template argument list of this other helper object called argproxy. Argproxy encodes the hash, as I mentioned before, in its argument list, but on top of that has this extra method. It's only going to be invoked at compile time, but it's what allows us this syntax here. So we can't define a free function that overloads the assignment operator, so I had to make it a method. That's why this is here. So the method is going to deduce a value type. So that's going to be like the value we supply as an argument. And then it's going to return a key value object. So the key value object is going to encode the hash again, that we're grabbing directly from the template argument list of argproxy. The value type, and we're also going to pass through it, we're going to forward this value. So we're going to extend its lifetime and then eventually return it so that we can initialize our arguments with it. So key value is another helper type defined somewhere above here. Really simple. So the hash part, the hashed key part, I should say, is just a template argument, and the only data that it holds is a reference to the value type, which we're going to use to extend the lifetime of a value. We're going to bind to it. When we use this little syntax bit here, what it results in is a key value object with the hash of our key and our type. I think it actually just becomes like a reference type actually. And then this value that we're passing through. So this whole list here is going to be of these key value types. So now that we have a key value type to work with, we can actually start searching for the hash which corresponds to the appropriate key value type and then return that value based on the target hash. So that's what this getArg function does. You saw it here. So here we're saying look for the hash that we compute for this key, and if you find it in args, all these args are going to be key value objects, then return the value associated with it. So just return the dot value of that key value object type. And I actually implemented two versions of this. So you see here that some of these getArg functions take a first argument, which is meant to be a default for if you don't actually supply a key value argument in the arguments list, and a version that doesn't take a default. So this is like a required version. So here you see that we can also construct this object when B and C are missing. Those are the ones with default supplied, and a version where we supply all of them. And here we actually have to supply A because otherwise it'll result in like a compilation failure because it's a required argument. So the way that I did that was I looked at the pack of arguments. I mean, I said it's a key value pair type, so obviously it could be not that if the first argument is a default value. So I looked at this key value pairs pack, and I checked to see if the first type was a key value object. So if is a, it matches the, essentially if it matches this key value template template structure. So if matches this structure, then we're going to call a version or an implementation for getArg that assumes that all these are key value objects. So the simple case. And then there's a second version. And again, I'm using a compile times code switch here. This if constant expression keyword is to basically use one section of code over another or whatever. It's like a compile time if else. In the past, you know, in C++ 11 or 14, you'd have to use enable if, like a sifnay substitution failure is not error, I think is what it's called, to remove certain functions from the function considered for overload resolution. But C++ 17 has this super nice feature where you can do that same type of thing, but I think a little nicer. So here I'm checking this compile time condition to see if one of the first arguments is a key value object template, and if it's not, then I'm assuming that that first argument is a default value, so an int, float, whatever. So let's look at these implementations. Basically what both of them do that's common is they recursively search for a key value object in this list with a hash that matches our target hash up here. So let's look at the getArg version first. That is here. Okay. So the way that it works is it takes a first argument, which is a key value. It deduces the hash and the value type. And then we're going to see if this hash value in the template argument list that we deduce matches the target hash. And if it does, just return the value of our key value pair. Pretty simple. If it doesn't, we're going to forward the remaining arguments to our getArg function called recursively to do the exact same thing on the next the next argument in our argument pack. So we keep doing this until we reach a terminal case. So the terminal case is where we have no other remaining arguments to look at. We just have this first template argument which has to be supplied, so the target hash. And if we get here, then it results in some compilation failure, which is ultimately what we want. So in the getArg with defaults version, the difference is we're going to do the same check for our target hash, but the only difference is our termination case. So if we hit the termination case, that means that we couldn't find a key value pair with the target hash. So just return the default value we supplied here. So pretty straightforward. So that covers these two guys. So the way that I selected whether to use this implementation or this one is with another helper, first type. So this is kind of equivalent to, like, I didn't want to use the standard library for this, so I could just like expand this type pack into a tuple and then use tuple element t to get the first argument. But you know, we're better than that, obviously. So I made this helper object called first type, which takes a variadic pack, and then made a specialization that just peels off the first type from that pack, cleans it up, or remove the reference, remove the const volatile qualifiers, and then made this little convenient accessor. So all this is doing is getting the first type in this pack and checking if it's a key value. So that this is actually a separate helper. So let's kind of like separate that out a little bit, just so it's clear. So we're using this helper to get the first type in this key value pairs variadic pack, and then there's this other helper which checks to see if it's a key value template, which is another really simple helper. So we define a base case that derives from false type, which is just this integral constant, bool, false. So integral constant, you can make these types of utility checking structs for compile time stuff. An integral constant is just a well, I'll actually just spell out what it looks like. It's easier that way. So if I was like to make my own integral constant thing, looks like this. Takes a template argument t and a value of that template type. Make a slightly different looking version. Integral constant, like this. And then it has a static const expr value here. It's like this. It's just assign the template value. That's it. But instead of using this, I opted to use the integral constant in the standard library just because it also supplies a bunch of other kind of nice to have things like some operators and such that allow you to access this value in different ways. It's simply syntactic sugar, doesn't really matter. But they exist, so I use them. So the base case is false type, which means that if we can't find a match, then T is not a key value template. But I guess the more interesting part is the partial specialization here. So if we can, if T matches this key value template pattern, and we can deduce a hash value in a value type T, so it's value type, so it's different than T, then our static const expr bool value is going to equal true. I'm going to do the same thing here. Just that it's explicit. I think the compiler is chugging a little bit. There's a lot of weirdo shit going on. Okay, but at least it's compiling again. Okay, so here's our key value check. I made a couple of other utilities that I used. I peppered in both those recursive functions to check to make sure that the arguments I'm supplying are actually key value objects. So all this is doing is looking at a variadic list of key value pairs and using a fold expression to evaluate that indeed all of them match this template pattern. Super simple. And I'm using this just to, I don't know, to get a static assert to fire off instead of looking at like a disgusting compilation output and trying to figure out what it is. It's not the best, but you know, whatever. You can see that I use that here, is key value check. And then I use another version of this to just exclude the first key value or key value type in the list, because that's going to be our default argument, and only check the second to nth. That's all this is. So what have I not explained yet? I think that's pretty much all of this. So what I didn't get to work, and I was hoping to on the stream, was, so I think I had it in here before. If I supply a junky value, like this, it gets ignored, but I wanted to be able to like check for it. I couldn't come up with a super elegant way to do this because it requires that you know all of the keys that you're going to be using, and that would require that each getArg knows about each possible key. I didn't want to do that because it makes it way uglier. So I was like, just hand wave over that, forget it, don't care, won't handle it. But something that was a little disappointed that I couldn't get to work in the stream was that if I supplied like a positional argument in the mix with my named arguments, it would just work right off the bat. And my default argument scheme kind of complicated that. So what I'm hoping to do is have another stream where I figure that out when I'm not as fried. I mean, I just went through a full day of work and now I'm doing this. So my brain is fucking spaghetti at this point. But I ultimately want to be able to achieve this. I figured, this is a decent stopping point. I mean, I got something that looks... It's not Python, obviously. This isn't just like a built-in behavior. You have to implement your own constructor for it. But if you really wanted to go out of your way to do this impractical mess of named arguments, this is like a pretty decent alternative. And the reason why, or I think the penultimate reason why it's like really good, kind of decent and not absolute shit, is that I made a little blurb here to compare the assembly when we turn on optimizations. Let's also get rid of IOStream. So what I'm going to compare here is that the assembly after optimization is the exact same if I was going to use the simple, argument list version. So actually, I put a comment here. I'm including all this in like the gist that I'm going to put on GitHub. But okay, so we can note that this assembly is indeed correct in terms of what I commented down here. And if I comment this out and comment this blurb back in, we see that the standard looking argument list version it compiles to the same assembly. So the compiler's smart enough to like optimize away all of our little tricks, despite the fact they're using this name argument paradigm, and result in the same code. It's amazing. And I'm pretty sure there's probably some case where like a more difficult case where maybe the assembly might expand into something else, maybe not as optimized. And here I'm using the arguments in like an addition chain, so it's kind of easy to optimize this case. I'm sure there's probably other cases where it's not. Maybe if like use like non-trivial types. So I guess for this video, something I didn't do in the stream was, let's say that this is a non-trivial type. First argument, string instead. Let's make this str instead. And now we want to just replace this with like a string literal. Initial string. This. Size. Because now this is a string. Going to include string. So I'm doing this just so it's like I have like an example of a non-trivial type working in this scheme. So yeah, we have a pretty similar assembly to what we had before because we're using this dot size. This might not be the best example because dot size is probably like a context per function. So let's do something even stupider maybe. I'll include C string, and then we will call standard strlen on the pointer, which should be null terminated, I hope. I mean, the compiler's still smart enough to figure this out, but can we get it? Alright, whatever. Let's leave that as it is. I want to show that it compiles to the same thing when we use a non-trivial type with our named argument scheme. So, initial string like this. Oh, sorry. It's actually out of order. So we could supply initial string here. Like this. And then we need to change the return statement to something similar. So I'll just keep it consistent. We'll do this. Why isn't it compiling? Oh yeah, because we changed the key. So now we see same exact thing. Doesn't even matter. So we can even do standard string initial string. Supply this as the value. Same thing. We can move it. Pretty sure this will be the same. Yep, same exact thing. So yeah, this is, I don't know. I was pretty proud of getting this done because I tried this in the past and I had to use a bunch of macros. I think maybe I did it before C++17 was like mainline. I was using like a version of Linux that didn't have the version of G++ in the repository list without like, you know, using a separate repository to get a version that'll compile C++17. But now with C++17, this is like pretty achievable. I mean, to my eye, this looks pretty close to Python. I mean, it's not, but, and again, as I mentioned, it's like extra work, but, you know, looks okay. So I hope you enjoyed the video. Hopefully I'll have a follow-up stream where I get this to work with positional arguments in the mix. That'll be really cool. And I will put a gist version of this on GitHub and include it in the link below. So thanks a lot. See you later.